Hello, everyone. This is a presentation on section 8.4, um, which is on homomorphisms and quotient groups and their relationship. And quotient groups. So, to begin with, given a homomorphism of groups, f from G to H, the kernel of f, which is denoted by ker f, is as follows. Ker f is equal to the set of all A and G, such that f of A is equal to 1, and that's for H multiplicative because the identity element in H is 1. Or kernel of f is equal to the set of all A and G, such that f of A is equal to 0, and that's for H additive. Okay. Remember, it's basically that f of A is the identity, right? But the identity is 1 in multiplicative groups, 0 in additive groups. So there's, again, that sort of discrepancy in notation, but, there it is. It's always there. Okay. So it's either this or this, when H is multiplicative or H is additive. So, for example, right, consider the group G, so examples. So consider the general linear group of 2 by 2 matrices over R. Right, what was that? It's the set of all 2 by 2 matrices A, B, C, D, such that A, B, C, D are in R, and right, the determinant of A, B, C, D, which is AB minus BC, is not 0. All right, that's a group, multiplicative group. And consider the group R star, right, which is the set of all x in R, such that x is not 0. Right, that's also multiplicative. Right, those are both multiplicative groups. And then from elementary linear algebra or matrix algebra, we know that, turn that off. From elementary linear algebra, we know that the determinant function, right, from GL to R star is a homomorphism. Right, because for square matrices, determinant A, B is determinant A, determinant B. For square matrices, right? Determinant of A, B is determinant A times determinant B. Squares such as 2 by 2. I mean, we know that from elementary linear algebra. We've talked about this homomorphism a few times, of course. So from elementary linear algebra, we know that's a homomorphism, and right, the kernel of the determinant map is what? It's the set of all A, B, C, D, such that the determinant A, B, C, D, right, is the identity element of R star, which is 1. A, B minus B, C is going to be equal to 1. Right, and that's the SL to R, right? The special linear group. There's the general linear group and the special linear group. So the determinant homomorphism from GL2R to R star, the kernel is the special linear group. So that's one example. So that's an example where the range is multiplicative. Here's an example where the range is additive. So consider the groups R star, right? It's the set of all x in R, such that x is not 0. Or, no, sorry, R star star. It's the set of all x in R, such that x is strictly bigger than 0, right? So, right, the interval from 0 to plus infinity, right, and that's multiplicative. All right, and the group R plus, which is the additive group of real numbers. Right, and the log function from R star star to R plus is a homomorphism. Right, because log AB is log A plus log B, right? So that old identity on log functions from high school, that essentially is saying that the log function is a homomorphism from this group to that group, and the kernel of the log function, right, it's the set of all x in R star star such that log x is equal to 0, right? Because that's the identity in R plus. Right? Here, the identity in the range is 1. That's a multiplicative group, R star. Right? So the determinant, the kernel of the determinant homomorphism is all matrices that go to the identity in here, which is 1. Right? Down here, this is the kernel is the of the log function is a set of all x in the range such that the homomorphism goes to 0 because that's the identity here. And of course, with this guy, the kernel is just 1. Right? Just the only thing that has log of x equal to 0 is x equal to 1. Right? So that's example number 2. Let's have like a finite group example. How about... Right, so we've seen this one before, but we'll say it again. F from Sn to Z2. Right? That's the group of all permutations of the set from 1 to n, and that's Z2. Right? Defined by f of an even permutation is equal to 0, and f of an odd permutation is equal to 1. That's a homomorphism. Right? And the kernel of f is equal to what? Well, it's the set of all pi in Sn such that f of pi is equal to, well, what's the identity of the range, right? This is, again, a multiplicative to additive situation, so it's 0, right? Which is the set of all even permutations. Right? It's the set of all pi in Sn such that pi is even right, which is equal to, right, AN, the alternating subgroup, right? Alternating subgroup. 4, F from the symmetries of the regular n-gon to Z2, such that F of a rotation is 1 and F of a reflection is 0. Right, is a homomorphism. We talked about this homomorphism when we did the section on even and odd permutations in Sn. So that was section 7 point something. I forgot. 7.5. Proven in section 7.5. This one is also a homomorphism. The dihedral group, the symmetries of the regular n-gon to Z2, where f of a rotation is 1, and f of a reflection is, oops, I got it backwards. F of a rotation is 0, and f of a reflection is 1. That is a homomorphism. We proved this, proven in section, so it was a section on homomorphisms. Imagine that was section 7.4. Yeah. Okay. But it's different. It's different than this. It's different than this. Remember, right? You can always label the corners of the 2 n-gon, right? On exam 1, you labeled the corners of the pentagon, right? And showed that D2n, which is a subgroup of S5, right? You could also do that with, any n-gon, of course, or any geometric object. So, like, for example, with the hexagon. So, right, rotation of 60 degrees, that's the permutation. 1 goes to 2, 2 goes to 3, to 4, to 5, to 6. So f of a rotation is 0 and f of a reflection is 1. We showed that's a homomorphism, right? And the kernel of f here is the subgroup of rotations are in the set of the n-gon. But when your n-gon is even, an even n-gon, this permutation is what? Right. So n is even. So this hexagon. This permutation, which is a cycle of length 6, is not an even permutation. Remember, it's an odd permutation because it's, I'm doing it backwards or forwards. 1, 6, 1, 5, 1, 4, 1, 3, 1, 2. All right, 1 goes to 2, 2. Yeah, this is right. It's written as a product of 5 transpositions. Right? The cycle of even length is written as a product of an odd number of transpositions. That's the definition of even and odd permutations, is how many transpositions you can write it as. And that's always even or always odd, the number of transpositions for any given permutation. So it's not exactly the same as this, because here we're saying f of a rotation is 0, but that's an odd permutation. So it's different than the even odd permutation for Sn, the even odd homomorphism for Sn. Okay, so similar idea, but not the same. Right, so D12, right, the dihedral group for the hexagon, is a subgroup of S6, but it's not the same as the odd-even homomorphism. So that's kind of interesting. So distinct examples. All right. Theorem. The kernel of f for any homomorphism is a normal subgroup of G. The kernel of f is always a normal subgroup of G. This is actually a homework problem, I believe, in section 8.2. Section 8.2. But it's presented as a theorem here. It's number 17. This is actually exercise number 17 in section 8.2. All right. So anyway, let's do a proof. Okay, so write k to be equal to the kernel of f, just for notational purposes, right? We need to show that ak, or not a, but gk is kg for all g and g. That is, so there's, again, different ways of characterizing this. That is, so the one way that I like to do it, that is, for every g in g and a in k, there is b in k such that GA, which is an element of the left coset, is equal to BG, which is an element of the right coset. Remember, two cosets, or no, I'm sorry, that doesn't hold true here. Okay, but that's all we need to show, right? That's all we need to show, is that for every G in G and every A in K, there is B in K such that GA is equal to BG. So not commutativity, but this pseudo-commutativity. Okay? All right, well, first, consider A in K, which was, remember, equal to the kernel of F. For any G in the group, okay, F of GAG inverse. Okay, let's look at that homomorphism and let's apply it to GAG inverse. Is equal to, well, because it's a homomorphism, it's F of G, F of A, F of G inverse, right? And then remember, the homomorphisms have that property where the inverse comes outside here. F of G inverse, like that, right? And then A is an element of K. So F of A is 1. Right? So this just becomes F of G times 1 times F of G inverse. But that's just 1 again, right? Therefore, this guy is still in the kernel. GAG inverse is an element of the kernel of F as well. Okay, say GAG inverse is equal to B, right, which is an element of the kernel. Right, so GAG inverse is equal to B, so GA is equal to BG as required. All right. And that's the relationship that we were going for. Okay. So the kernel of a homomorphism, always a normal subgroup. Okay. Let's see. Next. So this theorem is not quite as important, but it's interesting nonetheless. A homomorphism F from G to H is injective, right? That is 1-to-1. If and only if one moment. Okay, if and only if the kernel of f is equal to just 1 by itself. Okay, we know that f of the identity is equal to the identity. Okay, we know that that's always the case, right? So we always know that the identity is in the kernel. So kernel f is equal to 1, right, for multiplicative groups. Well, for H multiplicative. Or, you know, kernel of f is just 0 for H additive. Right, so a homomorphism is injective if and only if the kernel has order 1. Proof. So, for example, right? For example, injective homomorphism. Look at those ones that we were just talking about. Here we are. So the homomorphism, the determinant homomorphism from GL2 to R star. Of course, two very different matrices can have the same determinant, right? And you know, lots of different matrices can have determinant equal to 1, right? So I mean, like this guy has the same determinant as this guy, right? Just a very simple example, but I mean, you can put a 1 in here, right? 1a 0 0 a 1 0 y, you know, whatever the case. You could put an x up here or something like that. They all have the same determinant. Determinant is just a. So it's highly not one-to-one, right? Lots of infinitely many different matrices have the same determinant, and you know that includes determinant equal to 1. Right? Any matrix of the form looking like this, right? That's got determinant equal to 1. So infinitely many such things. So highly not one-to-one, and the kernel is not the identity. But this log function, right? The log function, the kernel is just 1. And we know that the log function is one-to-one, right? It's got an inverse function, the exponential function. And then these functions from Sn to Z2 and Dn to Z2, they are, of course, not one-to-one, because you're just saying f of a rotation is 0, there's a lot of rotations, or f of even permutations is 0, and there's a lot of even permutations, okay? All right, so let's get a proof of this. This direction. Or this direction is the easier one. Okay, say that, let me see. Yeah, that's this direction. So we'll do it by contrapositive. All right, say that the kernel of f, the order of the kernel of f, right, is not equal to 1. That is, there is y in the kernel of f such that y is not equal to 1. Right, so now, right, f of y is equal to f of 1, which is equal to 1. We're using multiplicative notation here, but y is not equal to 1. Right, so f is not one-to-one. Right, what does inject over one-to-one mean? It means whenever f of y is equal to f of x, this implies that y is equal to x. So here we have an example that's not. F of y is equal to f of 1 is equal to 1, but y is not equal to 1. Okay, so not injective. Back the other way. All right, so say that the kernel of f is equal to just 1. Right? There's just one element in the kernel, the identity. Assume now that f of x is equal to f of y. So, taking the inverse f of y inverse on the right, you have f of x, f of y inverse is equal to 1. Right? Just taking the inverse on the right. So, and remember with homomorphisms, that inverse comes inside there. Right? This is a homomorphism, so this becomes f of x, y inverse. So, f of x, y inverse is 1, meaning that, right, what does that mean? This guy is in the kernel. So, x, y inverse is in the kernel of f. But this is exactly the relationship that says that the right cosets are equal. So, as cosets, kernel of f, right coset x is equal to the right cosine, or coset. Oh, wait. Sorry. That's not what we were looking for. Xy is in the kernel of f, so, well, the kernel of f, well, is just equal to 1. Right, so xy inverse is 1. So, x is equal to y, as required. Right? So that's what we were looking for. Right? We assumed f of x was equal to f of y. F of x is equal to f of y, so fx, fy inverse is 1. So fxy inverse is 1, which means xy inverse is in the kernel, which is just 1, because that's what we assumed. That was our assumption. Right? So x is y. Homomorphism is adjective if and only if the kernel is just one element. And we have that example of the log function and the other functions upstairs. All right, so that's a less important result, but there it is. Okay, more important is the following. So now we're going to start relating homomorphisms and normal subgroups. Okay, we already know that the kernel is a normal subgroup. We proved that. But now, okay, consider the other way around. Let N be a normal subgroup of G. Okay, the function natural from G to G mod N, or not H, G mod N, given by natural of G is equal to the right coset NG, is a homomorphism with kernel in. Okay. Note this homomorphism is called either the natural homomorphism or sometimes people like the word canonical. Did I spell that right? I think it's with two N's. Yeah, canonical homomorphism. Right, so hence the usage of the natural symbol for music to denote that. All right, proof. Is a, surjective homomorphism. Surjective, meaning onto. With kernel equal to n. Okay, well, being surjective is just built into the definition because Gn is a set of all cosets, and right cosets Ng, or left cosets if you like left cosets. Right cosets Ng, and phi of G goes to Ng. So this is surjective by definition. Okay, now look at natural A, natural AB. This is equal to the right coset NAB. And because G mod N is a group, right, the operation of that group is the right coset for AB is the right coset for A times the right coset for B, which is natural of A, natural of B. All right, so you've got that homomorphism property. And lastly, that the kernel is N. Well, that's just part of the basic properties of cosets. All right. Because the coset NG is equal to N if and only if G is an element of N, right? So that's it. Right, it's the natural homomorphism, and the proof is very natural as well. Right, it's just all by definition, really. All right, so given a normal subgroup, this gives you a homomorphism. Right, given a normal subgroup N, this theorem gives you a homomorphism with the kernel equal to N, surjective homomorphism with the kernel equal to N. Given a homomorphism, surjective or not, where's that theorem? Given a homomorphism, surjective or not, the kernel of F is a normal subgroup of G. So homomorphisms give you normal subgroups, which are kernels of homomorphisms, which is the kernel of the homomorphism, and normal subgroups give you homomorphisms for which they are the kernel. And essentially, that's everything. This is the first isomorphism theorem. And we did this for rings as well, although, it's a little bit different here. First isomorphism theorem. If F from G to H is a surjective homomorphism, okay, if it's a surjective homomorphism, then the function phi from G mod the kernel of F to H given by phi of the right coset kernel of F G equal to just F of G is an isomorphism of groups. All right, that is H is isomorphic to G mod the kernel of F. So there it is. That's what homomorphisms really are. Homomorphisms really are another way of looking at quotient groups. And quotient groups are a way of looking at homomorphisms. So you can look at the things interchangeably. And that's a very, very important idea. As with rings, it was an important idea. It's an important idea here. We'll do a proof of this, and then we'll go over some examples. But there it is. Okay. Okay, so proof. Oh, one remark before the proof. If F from G to H is not surjective, right? I mean, this is for surjective homomorphisms. Then F from G to the image of F, which is a subgroup of H, right? Is surjective. Right? If you're not dealing with a surjective homomorphism, right? If F is missing part of H, you might as well throw that part of H away. I mean, you're really only using the part of H that G is hitting, right, via F. So you can always restrict yourself to surjective homomorphisms, right? There's rarely a reason not to consider non-surjective homomorphisms. Okay, so really we are talking about all homomorphisms. Okay, proof. Okay, the map phi from G kernel F to H given by phi the right. So let's call it K again. I get annoyed when it does that. Where were we? 8.4. Okay, so let K be equal to the kernel of F, just to make notation a little easier. The function phi from G mod K to H given by phi of the right coset Kg equal to just F of K is surjective because F is surjective. Right? Every element of H is of the form F of K. Right? Every element of H is of the form F of K. Or it's not F of K, F of G. Is of the form F of G for some G. So the coset, Kg, goes to F of G, right, which is every element of K. Right? Because every H in H is of the form F of G for some G in G, and phi of Kg is equal to F of G by definition. Of phi. So it's surjective. We also have to show it's injective. So let's show that phi is injective. Right, assume phi of Kg is equal to phi of Kh. Right, so this means that F of G, right, phi of Kg is F of G, and phi of Kh is F of H. So, F, doing the same thing we did before, right, F of G times FH inverse is 1, and that inverse comes inside here. So, F of GH inverse is equal to 1. So, right, GH inverse is an element of K, which was the kernel of F, the kernel of F. Right, we're calling it K just for notational purposes. Right, and that's exactly the relationship. That means the right coset Kg is equal to the right coset. Well, that means the right is equal to the right coset Kh. That was exactly the relationship. So Kg is equal to Kh when phi of Kg is equal to phi of Kh. Right, so this equal to this implies this is equal to this, as required. All right, now we just have to show that phi is a homomorphism. All right, this one is easy. Phi of Kg, Kh is equal to, right, well, because G mod K is a group, this is phi of the coset K GH, right, which is equal to F of GH. Right, that's the definition of phi. Right, which is F of G, F of H, right, because phi is a homomorphism, or F is a homomorphism. Right, but F of G is phi of the right coset Kg. F of H is phi of the right coset Kh. So phi of Kg Kh is phi of Kg, phi of Kh, as required. So that's it. All right, so for example, what can we do with this? All right, definitely some. Okay, so now note, go to or consider 8.2 number. So that's one of your homework problems. 8.2 number 8.1. Number, where is it? Number 25. All right, it's one of your homework problems. All right, show that SL2R is a normal subgroup. We know it's a subgroup of GL2R. We want to show it's a normal subgroup of GL2R just by showing that SL2R is the kernel of some homomorphism. Okay, so that's the homework, is to show that what was it, number 24? It was to show that number 24 or number 25. Yeah, show that SL2R is a normal subgroup of GL2R, and you do that just by showing it's the kernel of some homomorphism. So anyway, that's just a comment on that problem, but I mean it requires this discussion for it to be more meaningful. That's why I delayed the homework for section 8.2. All right, another example. Consider the group Q8. Right, the quaternion group Q8. Right, again, it's that group 1, -1, I, minus I, J, minus J, K, minus K, under the cross product. Product. Find all possible up to isomorphism, all possible groups H such that there is F from Q8 to H that is surjective. There is a surjective homomorphism F from Q8 to H. Okay, well, Q8, what are the subgroups of Q8? Essentially, we need to look at from the first isomorphism theorem. Right? From the first isomorphism theorem, what are all the normal subgroups? Kernels are normal subgroups. They're kernels are normal subgroups. Kernels are normal subgroups, and every homomorphism gives you Every homomorphism gives you a normal subgroup, which is the kernel. And every normal subgroup gives you a homomorphism whose kernel is that normal subgroup. So it's just a question of determining what are the normal subgroups of G, or Q8 in this example. What are the normal subgroups of Q8, and what are the possibilities for H? Well, Q8 is pretty small, so, Q8 is pretty small, so there's not going to be too many possibilities there. Okay. Well, let's find all the normal subgroups of Q8. Okay, remember Lagrange's theorem. All right, that every subgroup divides the order of the group. So here this group's got order 8. So we're talking about subgroups of order 8, 4, 2, and 1. All right, so here's your subgroup of order 8. Subgroups of order 4 are the subgroups generated by I, subgroups generated by J, and the subgroup generated by K. All right, so order 8, order 4. All right, so for example, I is the subgroup 1, I, negative 1, negative I. For J and K, similar to that. And then those are all contain the subgroup 1, negative 1. That's the center of Q8. And that contains just the subgroup of 1, order 2. So that's all the subgroups of Q8. And in actuality, they're all normal. Q8's a really special group in which all subgroups are normal. In abelian groups, commutative groups, all subgroups are always normal. But with non-commutative, no, it's not the case. It's very rare that there are non-commutative groups for which every subgroup is normal. Q8 is one of them. So surprisingly, all subgroups of Q8 are normal. Okay, now look at their quotients. Look at their quotients. Q8 mod Q8 has order 1. Right, has order 8 over 8, which is 1. Right, so it's just the identity. Right, so in this case, Q8 mod Q8 is isomorphic to just, I don't know, just this group, 1. Q8 mod I, or J or K, all have, or and, all have order, well, these guys all have order 4. And then Q8 has order 8, so all have order 2. So Q8 mod I is isomorphic to Q8 mod J. There's only one group of order 2. That's Z2. Right? Right, so those are all just Z2. And then, so that was order 1. So there's this subgroup, just H, where Q8 mod Q8 is just the identity. There's also Q8 mod I, Q8 mod J, Q8 mod K. Those are all just Z2. And then the last one is Q8 mod 1 minus 1. That has order 8 over 2, which is 4. Right? There are two groups of order 4. Right? There's Z4, the cyclic guy, and Z2 cross Z2, right? But Q8 is non-commutative, so you remember that theorem from section 8.3 that was on the video lecture is not, the quotient can't be cyclic. Q8 mod the center can't be cyclic because that guy is the center, because 1, -1 is equal to the center of Q8, right? So Q8 mod 1 - 1 is isomorphic to Z2 cross Z2. And then the last guy, Q8 mod just 1, is certainly just isomorphic to Q8. So that's it. So all of the, we say, homomorphic images of Q8 are the identity group, that's one of them right there, Z2, Z2 cross Z2, and Q8 itself. Right? So that's all the possibilities for homomorphic images of Q8. Right? By the way, all of the orders of the homomorphic images, they're all divisors of 8. Right? Because the order of the quotient group is order of the group over the order of the subgroup. Order of the subgroup divides the order of the group, and therefore you have that. Okay. One more theorem in section 8.4, but I am going to post this one now, and then go online on Blackboard to answer your questions, and we'll finish up the video lecture for section 8.4, just one more theorem after that class. Okay? All right, so signing out for now.